Hello everyone and welcome back to this series of videos on the Solow growth model. Specifically in this video, we are going to focus on how to derive algebraically the capital steady state, implementing the Cobb-Douglas production function. For those of you who wish to go through why the Cobb-Douglas production function is the best choice for the Solow growth model, you can refer back to the videos on this playlist from 7 to 11. Let's start off with what the Cobb-Douglas production function would look like in per worker terms. So we would just have this small kt to the power of alpha, which is the capital share of output, and what this small k stands for is the capital per worker, so big K over L. So this is what we're going to use, and this is what we're going to focus on. A quick note is that here we are assuming that there is no technological progress, so that our technology factor A is equal to 1. So let's look at what the capital accumulation equation would look like. So using our general form where we have the production function, our small yt, we just need to substitute in what we mentioned previously about what yt would be, which is k to the power of alpha. And so now what we have to do is start to rearrange it so that we can have something that we can start interpret. Specifically, we want to get to a point where we can define the change in the level of capital as kt plus 1 minus kt, meaning that the change in the level of capital is equal to the difference between capital tomorrow and capital today, of course. And why do we want to achieve this? Because we know that this in the steady state is going to equal to 0 because capital in the steady state doesn't grow. So we're going to start by opening up this bracket so that we get this extra kt term, which is quite useful for our purpose because we are now going to subtract kt from both sides so that on this side it cancels out and it gets moved to the other side. And we already have our kt plus 1 minus kt equals skt to the power of alpha minus delta kt. And we can now plug in this identity that we defined so that this becomes our delta kt. And we can see that now this is equal to savings rate times production function minus depreciation rate times capital today. And if we think about it, we are kind of back to our original intuition that we also mentioned in previous videos, where we say that the change on capital, so the additional capital that we have today comes from the extra investment over the depreciation that occurs on the capital stock that we already have. Again, we said that in the steady state, capital is constant, meaning that our change in kt is going to equal to 0. And specifically, it means that our capital tomorrow is equal to our capital today. And now, for simplicity, we are going to refer to capital in every period as k star. As in the steady state, capital doesn't change, we can use the same letter for all of the levels of capital. So that we are going to take back this equation. We are going to say that delta kt is equal to skt to the power of alpha. Actually, we just mentioned that we need to have k star, so let's stick with what we said. K alpha, k star minus delta k star, and this is equal to 0. So since we've got this equation, we are now going to bring delta k star on the other side by adding it, apologies, on both sides, so that we have that sk alpha is equal to delta k. And this is exactly the intuition of a steady state, meaning that on this side, the savings rate times the capital stock, but it's not really the capital stock, k to the power of alpha is our y, right? Is our output. So this would represent the investment per worker. And as we've already derived the intuition in the previous video, in the steady state, this is going to equal to the depreciation of capital, meaning that the number of new machines that we buy is equal to the number of machines that will break down. And now what's left for us to do is to solve for K star. In order to solve for K star, we are going to divide both sides. So starting from K star alpha equals to delta K star, we are going to divide both sides by K star, since we want to bring K star on one side only, so that on this side it simplifies out, and on this side we're left with K star to the power of alpha over K star. As we know, we can rewrite a variable that is on the denominator as on the numerator as K star to the power of -1. And since we are multiplying two factors with the same base, we can use the rule of indices and add alpha plus -1, so that we can rewrite it as S that multiplies K star to the power of alpha -1, which equals delta. Now, for rearrangement purposes, I am going to bring the K to the power of alpha -1 on the other side by dividing both sides by it. And the reason why I'm doing it is because since we know that alpha is between 0 and 1, having alpha -1 as a, let's say, as a power means that we are facing a negative power. So alpha -1 would be less than 0, and this is not ideal for economics interpretation. So I'm just going to bring this to the other side. And at the same time, I'm also going to bring delta on the other side. So what do we have? On the left-hand side, we have S over delta. And on the right-hand side, we have K star to the power of, so actually let's do one extra step, 1 over K star to the power of alpha -1. Again, to bring it to the top, we can basically elevate it to the power of -1. And if we multiply -1 by alpha -1, we obtain 1 minus alpha. So that we can say that K star, and I'm actually now rewriting this as if it's the left-hand side and this as if it's the right-hand side for simplicity purposes. K star to the power of 1 minus alpha, since we brought it up, is equal to S over delta. And now in order to get rid of this power, we just need to multiply, or basically elevate, both sides to the power of 1 over 1 minus alpha. Why is that the case? Because so in this side, by the rule of indices again, so there is a little bit of playing with the rules of indices here, but it's quite intuitive once you practice it a couple of times. The reason why we do that is because we know that if we elevate something to another power, the two powers get multiplied together. So if we do 1 minus alpha times 1 over 1 minus alpha, this is going to simplify out, and it's going to give us 1. So that on the left-hand side, we are left with the simple K star, which is going to equal to the savings rate over the depreciation rate, everything to the power of 1 over 1 minus alpha. So this is, algebraically speaking, the level of capital stock that we would, per worker, that we would achieve in the steady state. And as we can see, it depends on the capital share of output, the savings rate, so how much people, how much of the actual output is reinvested into new capital, because we know that savings equals investment, and on the depreciation rate. So how does this depreciation rate affect actually, how fast is capital depleting, and how will this affect our capital stock in the steady state? And this equation can usually be applied with numbers as well. And thanks to it, we can also derive the output per worker in the steady state. But this is something we're going to do in a subsequent video.